Hello everyone. So in this video, I will be talking about how you can write balanced half equations and also add them together to get an overall equation. Now I'm going to cut back on the content and just make this really simple. So these are just the simplest examples. We're not going to talk about the acidic conditions this year, and we scale up next year. So this is dot point 13.3. Okay, so half equations. The two processes, the oxidation and reduction, in a redox reaction can be represented using half equations. So as the name suggests, the half equations do not represent the whole thing, it just represents half. So it either represents the oxidation, which is the losing of electrons, or reduction, which is the gaining of electrons. So if we go back to this example, remember that magnesium loses 2 electrons here and the hydrogen ions gain 2 electrons. So you can actually represent these two processes using equations. So losing electron is oxidation. So oxidation is going to be Mg going to Mg2+. So you can see here, now in order for Mg to become Mg2+, the what am I talking about? The product has to have 2 electrons so that the charge is actually balanced. So if electrons are lost, then electrons will be shown on the product side. So gain 2 electrons. And reduction, it's going to be H+. Now you're going to need both hydrogen here because the product is H2s and you need to make sure that the equation is balanced. So H+ going to H2. And in order for this to happen, the hydrogen ions have to gain 2 electrons, so electrons will be on the reactant side. So these are examples of half equations. If I add these two half equations together, I will get the full equation or the overall equation. Okay, so the first thing that you need to be able to do is to write the half equations if I give you the overall equation. So I have 3 examples here. And also I want you to identify the oxidizing and reducing agents just for practice. So I had some steps. Once you get very good, you're not even going to have to follow the steps, but since this is a start, it's probably a good idea. So the first thing you probably want to do is to identify the conjugate oxidizing reducing agent pairs. And you don't necessarily need to know which one is the oxidizing agent and which one is the reducing agent to be able to do this. Basically, you just need to match the substance. So copper ions going to copper, that's going to be your first pair. So I know that I will have copper ions going to copper. And the second pair is going to be zinc going to zinc 2+. So zinc going to zinc 2+. So that's step 1. The next thing I'm going to do is I'm going to set the pair up, which I have, and I'm going to try to balance these half equations using electrons. So in order for copper 2+ to become copper 2+ must gain 2 extra electrons. So 2+ and plus 2- will equal to a charge of 0. Similarly, in order for zinc to become zinc 2+, it must have lost 2 electrons. So I'll put 2 electrons on the product side in this case. Step 3 is to add states. Now, states are very important when you write equations. Unless the question specifically say that you don't have to include them, you need to make sure that you do so. And this is very simple because the states are already given in the full equation or the overall equation. So you just need to copy them, I guess. And once you have written your half equations, you also want to answer the questions. In this case, you need to identify the oxidizing reducing agents. You also need to work out which one of these is reduction and which one is oxidation. So if you see electrons on the reactant side, that is the same as gaining electron. So gaining electron is reduction. Okay, so that's gaining electrons. And if you see electrons on the product side, that's losing electrons. Losing electron is oxidation. Okay, so that's reduction and that's oxidation. Now the substance that undergoes reduction is called the oxidizing agent. So oxidizing agent undergoes reduction. And the substance that undergoes oxidation is called the reducing agent. So this is the reducing agent. Okay, so that's example 1. Let's continue with example 2. So once again, I'm going to follow the steps. I'm going to start by identifying the conjugate pair. So I'm going to go, in this case, from, that's not that's not a coefficient, okay? That's just example 2. So I'm going to go from Cl2 to Cl minus. That's my first pair, conjugate pair. And my second conjugate pair is Ag plus silver ion going to silver. Okay. And now I've already set up the equation. I'm just going to balance it. So in order for Cl2 to go to 2Cl minus, it must have gained 2 electrons so that it becomes more negative. So the electron will be here. This L looks really weird. Okay, and in order for Ag plus to become Ag, it must have lost 1 electron. So it looks like that. And now I'm going to add state. So chlorine's a gas. This is aqueous. Silver ion is aqueous, and this is solid. And then label. So the first one is gaining electrons. I lost my train of thought there. So it's reduction. And the second one is losing electrons, so that's oxidation. Okay, so the substance that undergoes reduction is the oxidizing agent, which is going to be chlorine gas, and the substance that undergoes oxidation is the reducing agent, which is Ag plus in this case. Okay, so that's example 2. One last time, we're going to look at this one, which I haven't balanced, so that's not good. So I should balance it, I guess. All right. So once again, we're going to start by identifying the conjugate pairs. Now you don't actually have to use the coefficient in the overall equation when you translate the overall to the half equation. So I can just go PB 2 plus to PB, and that's fine. We'll talk about why the coefficients are there later. And the second conjugate pair is going to be Al going to Al3 plus. So that's all I have to do. You can do 3Pb 2 plus going to 3Pb if you want, but you don't have to. And that's going to make everything bigger. So now I'm going to balance the equation. So you have Pb2 plus, you need to add 2 extra electrons to become Pb. And if you start with aluminium, you need to lose 3 electrons to become aluminium 3 plus. And then I'm going to put in states. So that's this. This is solid, and that's aqueous. And then I'm going to label. So reduction is gaining of electrons, and oxidation is losing electron, which means that Pb2 plus is going to be the oxidizing agent since it undergoes reduction. And aluminium is going to be the reducing agent since it undergoes oxidation. Okay, so that's writing half equations from overall equations. Yep, I've labeled. The second thing that you may have to do is if I give you the 2 half equations, you need to be able to add them together to get an overall equation. And the key here is that when you add the 2 half equations together, the number of electrons have to cancel out. So before you can add them together, you have to make sure that you balance the number of electrons. And also the other thing is when you add 2 half equations together, what you get is actually an ionic equation. You're not going to see spectator ions in a lot of these redox equations. So even if you go back to this example that we did, obviously there has to be an anions that combine with aluminium ions, but it's not shown here because it's a spectator ion. Okay, so let's talk about what I meant by adding 2 half equations together to get the overall. So this is the first example. So this is the opposite of the previous question. This time I gave you the reduction and the oxidation, and you need to add them together to get the overall equation. So step 1 is to balance the number of electrons. And you can see that the number of electrons are not balanced. There are 2 electrons in the reduction and 3 in the oxidation. So in order to balance the number of electrons, you're going to need to multiply the half equations until you get the lowest common multiple of 2 and 3, which is 6. So what I'm going to do is I'm going to multiply the reduction by 3. So I'm going to get 3 SN4 plus 6. So multiply the coefficient of everything by 3. 6 electrons going to 3 SN2 plus. Now, because this is just an intermediate step, I'm not going to bother with steps as of now because I'm going to have to rewrite this anyway. And I'm going to multiply the oxidation by 2. So I have 2 aluminium going to 2 aluminium ions plus 6 electrons. So now my electrons are balanced. I can add the two half equations together. And this is actually very similar to simultaneous linear equations in maths, that the electrons will cancel out because you have 2 electrons in the reactants and 2 electrons in the product. So what you're going to end up in the overall is 3 Sn4 plus 2 Al, or aluminium, going to 3 Sn2 and 2 aluminium 3 okay? And then obviously you don't have to do this step because this one doesn't have any repeating species, I mean except for the electrons, but you can already cancel it out beforehand. And then you can add states in. So I'm going to use the state that was given to me in the question, and you can see that your equation is balanced because of the charge and also the number of each species. So 3 Sn, 3 aluminium. The overall charge on the reactant side is actually 12 plus in this case because 3 times 4 plus. And the overall charge on the product side is 6 plus 6 plus, which is also 12 plus. So the overall charge doesn't have to be 0, but it has to be equal to each other, the reactant and the product side, I mean. All right, let's do another one. So once again, I'm going to start by checking whether the electron number is balanced or whether I need to multiply the half equations. And I think I have to multiply the reduction in this case because that's 1 electron and that's 2. So I'm just going to multiply the reduction version by 2. So I'm going to have 2 Fe3 plus 2 electrons going to 2 Fe2 plus. So just like maths, treat this as like a bracket, so you have to expand and you have to multiply the 2 with every term in the equation. And now I think I'm ready to add the two equations together. So the electrons will cancel out, 2 in reactant side and 2 in product side. So you have 2 Fe3 plus cobalt going to 2 Fe2 plus cobalt 2 plus. Okay. And then there are no repeating species except for the electrons, which I already cancelled. And then you can put states in. So that's aqueous, solid, aqueous, aqueous. Let's do a quick check to see whether the charge is balanced. So the charge on the reactant side is 6 plus, and the product side is actually 4 plus 2 plus, which is also 6 plus. So the charge is balanced, and this is my overall equation. Let's do another one. So this one is actually looking very interesting because you have multiple species present. I'm not going to talk about this kind of redox reaction this year. Well, we leave that for year 12. We're just going to focus on balancing this year. Okay. So again, if you look at the number of electrons, there are 2 electrons in the reduction and, sorry, 4 electrons in the reduction and 2 in the oxidation. So I have to multiply the oxidation by 2. So I'm going to have 2H2 going to 4H plus and 4 electrons. And I'm just going to rewrite the reduction just so that to make it easier for me to see. So O2, 4H plus, 4 electrons going to 2H2O. So I'm going to add these two half equations together because my electrons is balanced now. And you actually can see that beside the electron, you can also cross out the hydrogen ions. This is what I mean by cancel any repeating species. So what you have left actually is just O2 plus 2H2 going to 2H2O. I'm going to put states in. And this is actually the combustion of hydrogen as a fuel in oxygen. So hydrogen plus oxygen basically reacts to produce H2O, but this is a redox reaction and really there are 2 processes happening. The oxygen has gained some electrons and the hydrogen has lost some electrons. Okay, last but not least, we're going to look at this one. So there are 4 electrons in the reactant side on the reduction and 24 in the product on the oxidation. So what I need to do is I need to multiply the reduction by 6 so that it matches the number of electrons in the oxidation. So I will have 6O2 plus 24H plus and 24 electrons going to 12. I really hope I did this correctly. H2O. Oh yeah, that'll be fine. All right, and now I'm going to add this together. So the electron will cancel out, but you also can cancel out the what am I looking at? There is something that's not right. I think I forgot to add 24 electrons in here. Yeah. There's supposed to be 24 hydrogen in the in the question that I forgot to add. So the hydrogen will cancel out. And the other thing I want to point out, I'm just going to rewrite this first. So you have 6O2 plus C6H12O6 plus 6H2O going to 12H2O and 6CO2. So you can also simplify. So if you have 6 water on the reactant side and 12 on the product, you can simplify it by subtracting 6H2O on both sides. So you're just going to end up with this 6H2O and 6CO2. Now, I'm sure the biology students would have recognized by now that this is cellular respiration, or the breaking down of sugar in oxygen. And cellular respiration is a redox process. There is a flow of electrons, hence electron transport chain. For those who don't do bio, just ignore what I just said. Okay, and that's it, and we are done. I think that's it for this one.